Once around the Garnet Star. So the Garnet Star is called Mu Cephei. It's in the base of the constellation of Cepheus the King, and a fairly unremarkable looking star at fourth magnitude. But you can see it under good lighting conditions with a nice clear sky. And if you do, you should notice the color. It appears to be a deep red color. Also exceptionally good to look at with a small telescope or a pair of binoculars. And the name, the Garnet Star, comes from a quote from Sir William Herschel. It's often called Herschel's Garnet Star. William Herschel noticed this star, and it wasn't in any of the catalogues at the time, so it had been missed in the first pass. And he said about it, a fine deep red garnet colour, and then such as the periodical star O Ceti, which is in fact Myra, and we'll look at Myra in another video. It was numerous astronomers also gave it names. Piazzi, the discoverer of the asteroid series, called it Garnet Sirius, which I suppose also means the Garnet Star. A little bit later, 1848, John Russell Hind realized that Mu Cephei, the Garnet Star, was a variable swinging by about a whole magnitude from its peak at 3.7 going down to nearly 5 sometimes. And records of this have been tracked for a very long time. It's been recorded continuously since 1881, so there's a tremendous wealth of data on it. Now, in terms of distance, things get a little bit more messy. The Hipparcos satellite measured the parallax angle by looking across the baseline of the Earth's orbit to see how much stars had moved against the background of distant stars, and it came out with 0.55 milliarc seconds. That's quite a tiny number. A milliarc second is a thousandth of an arc second, which is a 60th of an arc minute, which is a 60th of a degree. So this is a tiny fraction indeed. And really, Hipparcos was actually only accurate to stars that were much nearer than this, perhaps 500 light years, because 0.55 milliarc seconds gives a distance of 5,870 light years. So really pushing the limits of accuracy way beyond what was reasonable. Now, other surveys, including the Gaia satellite in its data release 2, have given lower numbers. So the Garnet Star may be closer than this upper limit of around 6,000 light years. But those estimates have varied quite tremendously, actually, depending on the basis. I think I trust the Gaia data, but some of the other data has given it much lower numbers indeed. Now, one thing that we do know about it is that it's moving, and moving very fast indeed, compared to the average velocity of the stars in its neighborhood around the galaxy. It's got an extra 80 kilometers per second, 80.7. So it's classed as a runaway star, and this suggests that it was formed in a large star cluster and underwent some sort of gravitational interaction. A gravitational slingshot in multi-star systems can eject members, and in fact this is what happens to star clusters as they get older. They have more and more of these near-miss collisions, which tend to hurl stars out of the cluster. So they boil stars off in all sorts of random directions with different speeds. So it seems likely, and this makes sense because actually, as we will see, this is a very, very large star, and you tend to only be able to get large stars formed out of big clouds of gas and dust, and they tend to form large star clusters as a result. So what do we know physically about the Garnet Star? Well, it's actually one of the largest known cool supergiants. Cool, low temperature on the surface because it is swelled up to an absolutely enormous size. And again, we have some different estimates for the size. Some of them have been by directly trying to measure the apparent size through an instrument and have given numbers in the range 19 to 21 milliarc seconds. So you can see that's vastly greater than that parallax number. So it gives you a suggestion as to how difficult using parallax might be. But the most recent figures are a bit lower, 14.1 milliarc seconds, and that was with a modern interferometer, which is able to actually see the star at this tremendous resolution. We get numbers, therefore, that translate to sizes in the range 1,250 to 1,650 times the radius of our sun. This is enormous. It would go out and engulf the entire inner solar system. And in fact, the planet Jupiter, its orbit is narrower than this star. So if it was where the sun is, then the inner planets and the king of the planets, Jupiter, would be gone. That's absolutely enormous. When we look at the star, we don't just see the light and the color, we can also split it up using a spectrometer to get an idea of the detail of which wavelengths are being emitted and absorbed by gases and molecules surrounding the star. And this gives us a temperature reading of around about 3,700 Kelvin. So I've definitely red in color. The peak of the emission is in the red part of the spectrum. You can see that in the chart on the right there. And you can also see quite a few absorption bands. These are characteristic of these cool giant stars. They have a cool enough atmosphere that molecules can form, and so you get these characteristic wavelengths bitten out of the spectrum like this. And it's fairly stable in this temperature range, and so it has been used as the reference star for the M-type, M2 classification for these red stars for a long time now. And as I say, it is a supergiant star. Up at the top right-hand corner of the Hertzsprung-Russell diagram there, right at the very high power output and low temperature end of things. And we think it's about 10 million years old, with a mass around 20 times the mass of the sun. Now, these large red giants and red supergiants don't have a particularly tight grip on their outer layers. They're so huge that the force of gravity at the edge of the star is much reduced. And so they tend to be losing mass outwards, very, very high solar winds or stellar winds coming away from them. And it's been calculated that every million years, about a fifth of a solar mass is being lost by the Garnet Star. And so with an age of 10 million years and losing a fifth in that every million years, you reckon that it's probably lost 5 solar masses and probably began life with a mass of 25. Very simple calculation, and seems to fit with our understanding of the evolution of these things. But a 20 to 25 solar mass supergiant, 10 million years old, is very much coming to the end of its life. The chart on the right is for a 25 solar mass star. So perhaps the Garnet Star has now come down a little bit, down to 20, and will live a little longer than the numbers in the chart on the right there, as it burns through the different stages of nuclear fusion, turning hydrogen to helium to carbon, and then on through the other elements down to the point where it builds an iron core. And we know that the Garnet Star is already through that hydrogen conversion stage and is beginning to convert helium into carbon. So if those figures were correct, then it's probably only got 500,000 years of helium burning, and it may be partway through that already. And then really the other stages don't last any time at all. You can see carbon burning 600 years, neon 1 year, oxygen 6 months, silicon just a single day. So it's within perhaps 200 or 300 million years of the end of its life. Um, Probably not tomorrow, though. So when it starts to get through to producing these heavier elements, it is going to go through further evolutionary stages. It'll probably become a blue supergiant, heating its outer layers up again, and it then may blow away the outer remaining hydrogen completely, exposing the inner helium layer. And at that stage, we would call it a Wolf-Rayet star. But eventually, once the process runs to completion and the iron core builds up, things will go wrong. It will no longer be able to liberate energy in the core. So the core will collapse, and then a supernova explosion will occur. The core collapses down dramatically, and in this case, probably all the way to a black hole. And this gravitational collapse frees up an awful lot of gravitational potential energy, probably also creates a storm of neutrons and neutrinos and gamma rays, and those rip out through the star and blow the outer layers apart in an enormous explosion. And depending on exactly the way that this decides to explode, we'll either see a type 2N, type 2B, or type 1b or 1c supernova. These are the characteristic spectral types from the helium emissions and the other elements that are present. None of these would really see very much by the way of hydrogen, because the unused hydrogen will have been blown away before that. And the result will be a black hole. So it's extremely likely that that's what will result. Now, we talked a little bit about the magnitude of the star, and we talk about this in many of the videos. Relatively modest, magnitude 4 to the eye. But these magnitudes were invented by the Greeks, and they had first magnitude being the brightest, second, third, fourth, fifth, sixth being the faintest that you could see. And these numbers really were just judged as an estimate by eye to begin with, and the stars were classed as first, second, third, fourth, fifth, or sixth in rank order. But it turned out, when it was being studied in the 1850s, 1856, Norman Pogson realized that the difference in the true actual brightness, once we had technical means of measuring the brightness to significant precision, he was able to show that the difference in brightness between a magnitude 1 and a magnitude 6 star was in fact a factor of 100. And so he proposed formalizing the system by taking the 5 steps that you have from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. That's 5 steps. And if you take the 5th root of 100, then each step is a factor of the 2.512 in brightness. And so you can commonly refer to that as 2.5. And so a magnitude 2 star is 2.5 times fainter than a magnitude 1 star, 6.25, and then about 16, about 40, and about 100. And it's fairly easy to remember those numbers and gives us a good rule of thumb for the brightness. But you can get very mathematical about it and start to use these numbers in sophisticated ways. One of the features that is often quoted about a star is its absolute magnitude. And its absolute magnitude is a measure of its power output, because it's the apparent magnitude that you would see if you were standing 10 parsecs away. And a parsec, you often hear in astronomy, is 3.26 light years. It's the distance at which that distance measuring method, the parallax method, with a baseline of the diameter of the Earth's orbit, will give you an angle of 1 arc second, 1/3600th of a degree. So that's 1 parsec. And for convenience, just to make the numbers plausible, absolute magnitude is calibrated at 10 parsecs. So we can do some numbers with this. I happen to know that the absolute magnitude, the power output of the sun on this scale, is plus 4.83. That's relatively dim. Remember, large numbers in magnitude are faint and lower numbers are bright. And the Garnet Star, well, that comes in at negative 7.6. So it's actually 12.43 magnitude steps brighter than the sun when viewed from that standard distance. That would be the ratio between them. And so we can use the magnitude rule, 2.512, doing it accurately, to the power of the difference in magnitudes, 12.3, gives us 93,809. And so the Garnet Star power output is 93,809 times the luminosity of our sun. And so essentially 100,000 times as powerful. That's a very, very substantial figure. But we can do more. We can also realize that the inverse square law of distance and the total power output allow us to relate the apparent magnitude that you see and the absolute magnitude and how far away things are. This is because the light spreads out over a sphere and so drops as the surface area of that sphere, which is 4 pi r squared. So you have to have a factor of 1 over 4 pi r squared into your calculations, and you can infer the distance. Now, of course, this does depend on you not having any intervening clouds of gas and dust to reduce the apparent brightness of your object. So if we take the Garnet Star, which has an apparent magnitude in the star catalogues of plus 4.08 and an absolute magnitude of negative 7.6, that difference is 11.68. We take our magic factor of 2.512, the fifth root of 100, and raise it to the power of 11.68, and we get 47,014. So that's the square of the distance ratio, because the distance drops as the inverse square. So if we take the square root, we get 216.8, and then we just have to multiply by that standard distance of 32.6 light years, 10 parsecs, and we get 7,068 light years for the distance. Well, that's greater than we got when we were actually using the Hipparcos parallax method, wasn't it? That was just 6,000 light years. So this is even higher. So what's going on? Well, it's that intervening dust. What we haven't allowed for here is that the apparent magnitude of 4.08 probably should have been brighter if it wasn't being blocked by several thousand light years worth of interstellar dust. And so actually, probably we've lost half a magnitude in our estimates of all of this. And if you plug in plus 3.5 instead of plus 4 into the calculation, then your distance estimate comes out in agreement. And so actually this is telling us how much dust there is in the intervening 6,000 light years. So it's quite curious how you can use one set of measures and get a difference and then go back round and estimate something entirely different. And indeed, talking of gas and dust, the Garnet Star itself has quite a substantial shell of gas around it, going out to about 1.3 times its radius, full of molecules at a temperature of just over 2000 Kelvin. So there's carbon monoxide, water, silicon monoxide being detected. Now, we detect these molecules because they're easy to detect, so there are an awful lot of others there that have more complex spectra and are much harder to figure out. These ones have nice, easy spectra and so are fairly easy to identify. So there's a lot of this molecular dust in and around this shell. And we think that the dust ring goes out rather than a completely spherical shell, it becomes into a flattened ring of dust going out 2 to 4 stellar radii. Contains dust, contains quite a lot of water. And you can actually see the two photographs on the right here. In the top photograph, the Garnet Star is the one near the top of the picture at the edge of this huge nebula of dust and gas with a lot of dirt and dust and material in there. Now, that's probably not the result of it having emitted this material. It's probably a nebula that it just happens to be passing nearby. Remember, it's got that high peculiar velocity, the runaway star. So it's probably just hurtling past this rather than actually being physically associated with it. But in the photo at the bottom, you can certainly see that there is quite a lot of diffraction and dust around the star. So we're pretty sure about this. So the Garnet Star, if you get the chance, do go and have a look at it. There's a lovely picture here to finish with. It's such a lovely color to look at through a telescope, and no picture on the screen can really do justice to it. So that's Herschel's Garnet Star. Thanks very much for listening, and I hope you enjoyed it.